that we formulate in order to study this problem. After that, I present two methods that we are using to solve the problem. The first one is the most used in this area. And the second one is our approach, and it's not very common in this area. We haven't found many results using interpol methods in epidemiology. And at the end, I will present some numerical solutions and conclusions. So the motivation for this problem was the emergence of a novel strain of influenza. It was used when I started my PhD, so I get a very good problem to working on. So we start working with this problem. There are several continuous time models used to study influenza outbreaks, but our approach is a discrete model. The idea for using a discrete model is because it is easy to compare data that is produced in discrete time with the output of our model. The identification of optimal control policies is also have been studied in continuous time, especially the using of treatment and isolation. So this is the idea for the model. We divide the total population in susceptibles, infected, and recovered individuals. This G is the people that were susceptibles and they get infected. Sigma is the recovery rate. In this model, we just consider delta is the mortality due to the disease. We are considering a single outbreak. That means that is like, for example, 3 months. That is the time that for an epidemic. So we don't need to consider births and natural deaths. With this idea, we formulate this model. So this is in G is people that get infected. 1 minus G is people that remain susceptible. Susceptible is like healthy people, so all of us could be susceptible. And this will be for the infected individual, we have the new infected, and also people that don't get recovered and people that don't die. R is the recovered individuals, and the expression for the function G is given in this way. So we have a new infection if we have contact with an infected. And these parameters are the infectivity for the people that is infected, and rho is the susceptibility for somebody that is healthy. Now our idea is include social distancing and treatment in the model as control policies. The idea of social distancing is how do you reduce your number of contacts when there is an epidemic. If you remember in 2009, there were several policies taken in Mexico. For example, they closed schools, they canceled public events, and many of us maybe take some measures like wash hands, don't go where there are many people, so that this is related with social distancing. And we consider treatment just like antiviral treatment, like Tamiflu or this kind of antiviral. So what we want to do is minimize the number of infected individuals by using a minimal effort in treatment and social distancing. In order to do that, we need to modify the previous model that I showed. So what we do is, in the new model, we include a new class of people, that is the treated people. So we consider that a fraction of the infected people, tau will be this fraction, get treatment. And we include a new parameter now that is sigma 2. The idea is that if somebody gets treatment, they will recover quickly than somebody that don't get treatment. So now we have one more equation, and also G is going to change a little bit. Because treated individuals, even though they have treatment, they are still infectious. But we assume that if somebody gets treatment, they reduce the infection a little bit. And also this X is going to be the social distancing. So 1 minus X is like a reduction of the probability to get a new infection. The meaning for this X, since this is social distancing, if X will be, for example, 0.2, that means that you will reduce your number in contacts or 20% per day. So if every day you meet 10 people, you will meet just 8. That is the idea for this parameter. So as I said before, we want to minimize the number of infected, and we are going to work in a final interval. This n is going to be our final time. We are working with 220 days because it's more or less the time for a single outbreak. And we formulate the problem in this way. We want to minimize the number of infected, and we need a minimal effort in social distancing and treatment, because we could say that people don't have any contact. So we need to find what is the value for x in order to reduce the number of infected. And these B2 and B3, they are weight constant. What that means is the relative cost of the policies. And the restriction for this problem is the model 2, that is the one that I presented before. So in this model, x and tau are our control variables, and the other variables s, I, t, and r, these are the state variables. So there are basically two ways to solve the problem. The first one, that is the widely used, is the contrary maximum principle. The contrary maximum principle gives us like the necessity condition for a solution to be optimal in an optimal control problem. The first thing that we need to do in order to solve the problem, we need to write the Hamiltonian. So this expression, this was just the one that was inside the summation in the previous slide. So in the Hamiltonian we have this one plus, here will be, for example, lambda 1 times s plus lambda 2 times e. So this y is all the state variables. For this Hamiltonian, we derive the necessity conditions. So they are given by the adjoint equation, that is just the derivative of this Hamiltonian with respect to each state equation. If somebody has worked with optimal control problems, here is a little bit difference, it's not a mistake. We don't have a minus because this is a discrete problem. So the only difference for the conditions in the discrete and the continuous time is that now we don't have a minus. The other condition is the transversality condition. The idea is that for this equation, the value of lambda in the final time is 0. And finally, we have the optimality condition. It's the same that when you were working in your calculus class. If you need to find a maximum or a minimum, the derivative has to be 0. So in order to solve this problem using Pontryagin, we use an algorithm that is called forward-backward algorithm. The basic idea is that we need to solve the state equation, that is the model that I present. We solve this state equation forward in time because we have an initial condition. We know at the beginning of the epidemic how many susceptible, how many infected, how many recovered. Usually we work with, for example, 1 infected and all the population susceptible. So we have the initial condition for the state equation, so we solve this one forward in time. For the adjoint equation, we solve backward in time because we have a condition at the end. So for this reason, it's called forward-backward algorithm. So this is like the first approach. The second one, that is the one that we are introducing in this area, is integral point methods. These methods were introduced by Karmapa in 1984. It was introduced for solving linear programming programs. It has a lot of application, but in this area of mathematical biology, it's not easy to find something using integral point methods. I just found one paper after looking for many times. So I think there is not too much application in this area. So the basic idea for integral point methods is that, contrary to the simplest method, it goes to the interior of the region. So it finds an optimal solution going for the interior. That's the reason why we call it integral point method. The first idea to solve the problem, we need to pose our problem as a nonlinear programming problem. So now we have f of y. In this case, y, we put together the state and the control variables. So we have now used one variable y, that is with all of the variables that we had before. And the quality constraint is going to be our model. We just rewrite this equation and we have the quality constraint. We could include here inequality constraint. This is one of the advantages of integral point methods. We could incorporate the inequality constraint in the formulation of the problem. So this y max is because we could have some upper bounds for the control. For example, we have some limits of doses of treatment per day, or we have some limits over the social distancing. So this is the problem. Now, instead of this summation, we could write the problem using norm. The norm 2 is the equivalent formulation for this problem. The basic idea for the integral point methods, instead of the Hamiltonian, now we have the Lagrangian. So basically it's the same. We have the objective function, we have the equality constraint, and we have some Lagrange multiplier associated with the equality and one Lagrange multiplier associated with the inequality. So instead of have adjoint variables, now we have Lagrange multiplier. And basically the necessary conditions now are related with this Lagrangian. We have the derivative with respect to y. When we have the derivative with respect to w, we just have this one. And the last one is the perturb complementarity condition. And we need that these will be equal to 0. And the main idea in integral point methods is that we solve this equation using a line search Newton method. So now what we do is that we solve the problem using both methodologies. The idea is to see what is working better. And also in terms of the epidemiological application, we want to compare 3 strategies. So we want to see what happened when we apply only one policy or what happened when we put both policies together. So the first strategy is only social distancing. The second one is only treatment. And the last one is both strategies together. So the first idea, when we compare both methods, you could see here with forward backward, we solve the first strategy in 52 iterations. We go to 11 iterations using integral point methods. Here we also have a very good reduction. And when we put both policies together, we have some problem with the convergence in the forward backward. But we could solve the problem using integral point methods. With this idea, we found that integral point methods solve the problem with a few number of iterations. So now we solve the problem using integral point methods, and we find some numerical results in terms of the epidemiology. So here, for example, we want to see the implication of policies when R0 is equal to 2.5. R0 is the basic reproductive number. What that means is that, for example, if R0 is equal to, if all of R are healthy people and there is a virus and some infected individuals get here, 2 of us will be infected. So this is the idea of the basic reproductive number. For the case of influenza in Mexico, it was around 1.4 or less. So this is like a high value, R0. What we want to see here is that when we apply the policies, this one is both policies together. This one, the red curve, is the final epidemic size, how many people will be infected at the end of the epidemic. So if we don't have any control, almost 90% of the population will be infected. This is for a high value of R0. We apply use treatment, we get a reduction, but there is a better reduction if we use social distancing. And this is even better if we use both policies together. So what we find is that social distancing is better than treatment, but both policies always is better. This is for a particular value of R0. So we do some simulation for different values of R0, taking values from 1.3 to 2.9. There is an epidemic if R0 is greater than 1. If R0 will be less than 1, we don't have an epidemic. So here always, both policies is better. For social distancing, use at the beginning, treatment is better. but for values greater than 1.4, that it was used the 1 for Mexico, social distancing is better. Social distancing could be better is because this is applied for all the individuals. In this model, we don't consider, but there is something asymptomatic individuals, for example. So social distancing will be applied to everybody. For this reason, it could be a best option. Some conclusion. So what I told before, we solve an optimal control problem using two methodologies, forward-backward and inter-call methods. We find that inter-call methods solve the problem quickly than the other one. And we also find that the use of single and dual strategy reduces the final epidemic size. For future one, the idea is to extend this model for an age group model. The idea is to divide the population in groups because, for example, if influenza has different impact for people in different ages. So we want to know how the policies should be applied in each group. So some acknowledgement to the grad school and the faculty and staff involved with this event. Computational Science Program, Carlos Castillo Chavez, special thanks to Sammy, who is the one that helped me a lot during the summer in the NTVR summer program.
Okay, so I have a question. So your conclusion is that the exact in 2009 that was the wrong choice of the policy, right? Antiviral would be better because R0 was 1.4.
It's like, no, I think it was a good policy.
But because if you look at your conclusion, can you go to the previous slide? It says when R0 is, but maybe I'm misunderstanding.
Yeah.
It says when R0 is 1.4, this is better, right? Does it? I can interpret it in two different ways. One, you don't know what happens when R0 is less. Two, you checked when R0 is equal to 1.4, antiviral is better. What is it?
Let me see the plot. You see this plot? So you said the beginning. Let me find.
Here, for 1.4. Yeah. So here the antiviral would be better, right?
Yes.
Take a chill pill.
Yeah.
So social distance is the wrong choice of the policy.
The problem is that maybe this is not the right value for R0. I don't know something.
Oh, okay.
What was the value for R0
Okay.
in Mexico?
It's hard to measure.
But you said 1.4, right?
Yes, it was like an approximation.
1.5.
Oh, so it could be 1.5.
Very hard to measure.
Okay.
It was used like to give an idea to the audience.
Okay, so
what it would be the R0.
Other questions?
Yeah, this kind of, in addition to being interesting from the research point of view, is this kind of research used to inform policy or to inform equipment, or to help organizations to devise treatments? What are the side benefits of doing this?
In this case, it's not like what kind of treatment will be better. We are just thinking about an antiviral treatment, and we assume that this treatment is really good, but we don't have like development of treatments.
This can be also for like, you want to spread the word about computational science. So one person has to convince at least 1.5 other people, right?
It will be less than one, perhaps.
Okay, thank you very much. Let's thank all the speakers. I think now we have a coffee break, right?